About topics regarding atoms and ionic bonds. Today's next session is pertaining to things that have to do with higher ionization energies. From our learning objectives, the higher ionization energies, second, third, fourth, etc., are needed to be discussed for any pair of elements. All right, this chart from the textbook shows some useful information regarding ionization energies past the first ionization energy. Recall that the ionization energy is that energy required to take an electron away from a neutral atom in the gaseous state. The first electron removed results in a cation. So the second ionization energy is the one that is being applied to remove the second electron. But now it's being removed from a cation. And so the second ionization energy will always be greater than the first one. So look at sodium for an example in the first column. The first ionization energy here, don't worry about the actual numbers. Yes, it's kilojoules per mole. Nobody's asking you numbers at the moment. But notice the second ionization energy, a great big jump. The second one is much more difficult to remove. It requires almost 4,000 kilojoules more than the first one. So that will be true for other elements as well. Magnesium has a much greater second ionization energy than the first. Aluminum has a greater second ionization than the first energy than the first. Remember also that the pattern with between elements in the third row or a given row is that when you're removing one electron from a 1s subshell, that's the s subshell in case of magnesium. Sodium is a third shell, 3s1. It's less energy than removing one for magnesium, this paired up full second 3s subshell. Okay, so whatever the case, removing the second electron always requires more energy. But keep looking down the pattern here, because if you're going to have the third, so this is ionization energy 1, ionization energy 2, and ionization energy 3 is removing that third electron from a +2 cation. That's an even greater amount of energy required. It's more difficult to remove an electron from a doubly positive ion. And so that's why these values increase as you go from the second one to the third one in each case. However, there's something else to be noted here. Clearly, there's a zigzag line in this chart trying to bring something to your notice. And that is that there's a huge jump in ionization energies between two values for every one of these elements at some place or the next. So let's see where that is and what pattern to make of it. So let's get rid of those extra lines for the moment. And the stair-step zigzag line marks the large jumps. Well, between the first one and the second one for sodium, between the second and the third for magnesium, between the third and the fourth for aluminum. Well, what explains that difference? Well, if you think about it, sodium loses one electron, and then you have a sodium ion, a sodium cation, and that is stable. And so if you're going to take the sodium cation and remove a second electron and have a sodium +2 cation, that's extremely unlikely. It's much less likely because this is so very stable that it's going to be extremely hard to remove an electron from that sodium ion. So that explains this big jump. Same thing true for magnesium. After you've reached the second, remove 2 electrons, losing one more electron to make a magnesium 3 cation, which is not likely. The magnesium 2 is just stable, just like the sodium single cation is. Removing the next one from magnesium is a big jump because it's far less stable. So you can tell that for each of these things, you reached a point where there's a very stable ion attained, and similarly for aluminum. So you can take away 1, 2, and 3 electrons, but to make aluminum 3, which is the typical cation for aluminum, but trying to take one more away from aluminum is far less likely, far more energy required, because that is just not stable to take away another electron. So there's an obvious pattern in ionization energies. When you reach a stable spot, the next electron removed is a much greater value in ionization energy. Let's see if we can use that pattern as we look at some other examples. Okay, so let's keep thinking about this and make some sense of it. The ionization energy definition, again, is the minimum energy required to remove an electron from a gaseous atom in the ground state. In other words, it's a measure of attraction of an atom for its own electron. So the first ionization energy, you take that amount of energy, and that ionization energy is I1, add it to X, and you make X into a cation in the gaseous state. That's what I1 is the first ionization energy. The second ionization energy then removes the electron from the cation, singly plus cation. We call that the second one. And I3 is the amount of energy you add to the doubly positive cation to remove it to make it a +3 cation. So the third ionization energy and second and first, how do they compare? Well, the third is always greater than the second is always greater than the first. So as we look at these patterns, how does that apply to other things? We're going to remember that each successive removal of an electron requires an increasing amount of energy because the amount of nuclear charge is always the same, but then you're pulling against fewer electrons. And so that charge is much greater, and the charged protons to electrons makes it much more difficult to pull away an electron the more times you take one off. All right, so here is a very interesting chart that I have to credit my colleague Dr. Pierce for having made. He took a bunch of data from some data source I can't recall particularly, and made a 3D chart that reflects the ionization energies for main group elements in the third row. So sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon across the bottom here. You'll see that. And the first ionization energy through the 7. So E1, ionization energy 1 through ionization energy 7. Now, we're not going to get to 7 very often, but they're always going to be increasing. So if you look at sodium, you go from 1 to 2 to 3 electrons removed. It always increases as you go. And that same thing would be true for argon, for 1, for 2, for 3 electrons being removed. But notice the pattern. For argon, they increase in a systematic way without having any gigantic changes. But the pattern that was shown in the zigzag line is represented in a 3D fashion differently here. So there's a big jump from 1 to 2 for sodium. There's a big jump from 2 to 3 for magnesium, a big jump from 3 to 4 for aluminum, a big jump from 4 to 5 for silicon. So when each atom has reached a point where you reached a very stable configuration, in other words, something with a full outer shell, then the next removal is going to be a much greater energy required for that ionization energy. So the pattern continues. If you keep looking for phosphorus, the next biggest jump is behind the one for silicon, and so on. So maybe that's a nice visual for you to relate these increasing ionization energies and where the giant leaps are between the different ionization energies. So think about it. In each case, though, you're going to get to a point where they're stable, and that's why the next removal is hard. So after you remove 1 electron from sodium, you get to an outer shell that's full. When you remove 2 from magnesium, you get to a full outer shell. When you remove 3 outer shell electrons from aluminum, you get to an outer shell that is full. And so each of those are very stable and then subsequently require a lot more energy to remove the next electron. Chlorine, again, actually is very much the same, although it's a lot more electrons till you get to that point. So if you're removing a lot of electrons from chlorine, it'd be very odd. But if you did, you would end up with something that is equivalently stable, a full outer shell. And so the pattern is that chlorine will have increasing difficulty for removal of electrons, but all of them will be progressively more difficult without gigantic breaks. Go back to the previous example or previous slide and you'll see that again. Chlorine, they just increase steadily as you go from 1 through 7 in this set of data, but there isn't a one where you go beyond the stable one when you do 7 for chlorine. Okay, so let's do this in the context of a couple of examples. Which one has a smaller first ionization energy, oxygen or sulfur? Think about it for a minute and see what you remember. The first ionization energy is how you pull one electron away from an atom, a neutral atom in a gaseous state. Is it going to be easier to remove it from oxygen or sulfur? It should be easier to remove from sulfur because why? The outer electron is in a different shell. It's in the third shell. Farther away from the nucleus, easier to remove, smaller first ionization energy. Oops, I did the letters backwards. Fix that. Oops. Ionization energy, or IE1. Now, which would have the smaller second ionization energy, lithium or beryllium? Looking at those two over there on the left. So removing one from lithium should be easy, but removing the second one will be hard. So for lithium, first ionization energy is going to be much less than ionization energy 2. Well, that's true for both of them. But which one is going to have a smaller second ionization energy? Which one is easier to remove the second one? Well, remember when you get to lithium as an ion, as lithium ion, that's very stable. So the second ionization energy will be very large for lithium. So the smaller one would be beryllium, because beryllium, by the time you lose the second electron, it's going to be beryllium 2, and that isn't as hard to do. That would be a larger energy change, but it's much more likely than removing one for the second one for lithium, because beryllium has reached a stable spot, and you've gone beyond the stable spot for lithium if you take away the second electron. Okay, now here's another one. This is a different graphical representation. We don't always like graphical things, but we need to think about them gradually. And we've got three elements: magnesium, aluminum, and potassium. Magnesium, aluminum, and potassium. And it helps us to think about these in this fashion if we can make sense. The first one is all kind of similar. The second electron is easier and harder for some, but the third one is drastically different for the red line. So which one is going to be most difficult to remove a third electron? So hardest to remove a third electron. That's what has to be the red line. Well, the red line then must correspond to the one that's stable after you remove 2, and so that should be magnesium. See if that's our first answer here. Whoops, backwards. Uh-oh. I didn't want to show you that yet. All right, so the blue one would be the one which has a steady increase from 2 to 3 without being dramatic. And the green one is, they're all kind of the same. So how do we make sense of these? Well, magnesium is going to be the red line, and aluminum and potassium are ones where they are increasing gradually. But what's the difference between aluminum and potassium? Potassium has a big jump from the first electron to the second one. The second electron, the second ionization energy should be much larger than it is, a much bigger change than for aluminum. And so there should be a steady increase for aluminum and a steady, similar progression, steady increase in ionization energy for aluminum, and a bigger jump for potassium. So let's see now that I can show you the answer. So the blue line should be potassium, where the second one is much higher than the first, and then the red line was magnesium, as I stated, and the green line would be aluminum, because the increase from one to the next is going to be a steady increase. That takes a little bit of thinking. Hopefully that makes a little bit of sense to you. Okay, let's see if we can find one more set of examples for you. All right, so if we're looking at our friend the periodic table, we can think in terms of position on the periodic table, but we could actually name these elements, that wouldn't hurt, and see if they're going to help us out. So the red element is the third one down in group 2, that'd be calcium. And it's not necessarily necessary to identify it, but let's do it anyway. Aluminum is the green box, and the fourth one down in the noble gases would be krypton. Now, which one is going to lose its third electron most easily? Well, does krypton lose any electrons easily at all? No. not krypton. So it's not going to lose any electrons easily because it's very stable to begin with, and it's going to be first, second, and third are all going to be very difficult. For calcium, when this one loses 2 electrons most easily, because then it will get to the third electron that is more difficult to lose. So losing the third electron is harder, for much more difficult. That's where the big jump is going to be for calcium, and that would be ionization energy 3. And aluminum, it's going to be a steady increase. Ionization energy 1 is less than ionization energy 2, and ionization energy 3 is still larger, but not a huge jump until you get to the fourth one. So aluminum would be our correct answer here. None are lost easily for krypton, easily. All right.